Hi, today we're going to talk about covalent bonding as opposed to ionic bonding and metallic bonding. So let's have a go. So covalent bonding is, we can figure out what it is based on the name, covalent, co meaning shared, valent is refers to valence electrons, which are the outer shell electrons. Now, bonding in covalent structures is for the same goal as in ionic bonding. Now, remember, in ionic bonding, what's happening is one ion is donating an electron to reveal a full outer shell, and the other ion is accepting an electron in order to create a full outer shell. So that way they get that octet, they get a full outer shell. Now, in the case of covalent bonding, what they're doing is they're sharing in order to have a full outer shell. Imagine this is chlorine, he's got 7, right? And he wants to bond with this other chlorine that's also got 7. Well, one can't donate. If one donated, I mean, it would end up with 6, wouldn't it? Right? If one lost an electron, end up with 6, which is terrible for it. That's not going to work. But what could happen is they could both share an electron each, and then both reach their 8. So chlorine here, 1, 2, 3, 4, 5, 6, 7, 8, and this chlorine here ends up with 1, 2, 3, 4, 5, 6, 7, 8. So then it ends up with a full, each of them end up with a full outer shell by sharing these electrons. And these are between two nonmetals. So if you think about the periodic table, it's only the nonmetals to the right that will have this, will bond covalently. The only thing to realize is that hydrogen, in this case, counts as a covalent compound or bonds covalently anyway. Okay, so just to kind of go through it again, chlorines or any two nonmetals can bond when they share an electron. This way they can each reach their octet. So why do things bond covalently versus ionically? What exactly is going on there? Let's have a look at this graph here. What we have here is electronegativity difference. So down here, the electronegativity difference isn't very high. So remember, electronegativity is the ability of the atom to attract electrons, right? So the difference between iodine and bromine is not very much, right? Whereas the difference between potassium and fluorine is quite a lot, right? So the difference is very high, yeah? Down here, it's probably, 0.4 or 0.3, and up here, it's probably 3.5, 3.25 or something, right? Now, percentage ionic characters. That means up here, these are very ionic bonds, and these are covalent bonds. So you can see here there's a very clear relationship between the electronegativity difference, right, and whether it's an ionic bond or not. The compounds that are ionic tend to have a big electronegativity difference, right, and the compounds that are covalent tend to have a low electronegativity difference. And you'll see here there are some that are kind of in the middle, right? They have some covalent properties and they have some ionic properties. So that's a bit complicated. You might deal with that in first year uni. But you can certainly see from this that a low electronegativity difference is covalent, a high electronegativity difference is ionic. So what's going on there? Now, if you imagine that the electronegativity difference between two atoms, in this case they're exactly the same atom, so there's no electronegativity difference. The pull between these two means that the electrons are equally shared. And if we're talking about sharing, then we're really talking about covalency, aren't we? We're talking about sharing electrons rather than donating, right? And as we work across to more polar, we can see that there's some pull, and the chlorine in this case, as opposed to the hydrogen, is taking the electrons for most of the time, but it's still sharing a little with this hydrogen, right? And over here we can see that the chlorine has taken the electron completely, right? It's taken it completely. So you can see that there's a pattern here. As the electronegativity difference, as the attraction of these electrons becomes stronger, the likelihood increases of one atom taking that electron completely rather than sharing it, and therefore you end up with this ionic character. I found this little cartoon which helps a bit. So if you imagine we have a weak pull and a strong pull, the electrons can be pulled over to one and become ionic. But if the pull was about equal, it would be definitely they'll be sharing that rope, wouldn't they? They'll be sharing these two electrons. Okay, that's it for today. Answer the question below, and I'll see you in class.